Hello students, good morning. Today we will try to discuss one of the important lecture of chemical kinetics, that is how to deduce the different units, explanations and calculations for any given type of reaction, that is called first order type of reaction, second order, zero order. What are the things given in your syllabus actually? And for that, we first try to learn what is the meaning of this word that is given here, rate law. How to represent this rate law, that is called rate expressions. And how to calculate the rate constant value for any given type of reaction. What is the meaning of order of reaction and what is the sense of molecularity of the reactions. All these things related to the same concept, the same framework. So we will try to enter in the frame where we will learn the rate of the reaction will depend to which extent of the any given molar concentration of the any given reaction. The important thing is about to learn whatever the reactant's concentration given, how we can know that the rate of reaction will depend upon which extent of any given molar concentration of the reactions. And for that, we have to be first try to attempt this term rate law and the rate expression. Okay, so first consider any given chemical reaction. Suppose a general reaction. Suppose a general reaction A, B, that will give you a C plus D with a different stoichiometric coefficients A, small a, B, C, D. That is, okay, that will be a coefficient of the reactions. According to this given reaction, we'll try to learn about A and B combined together in the ratio of small a and small b to gives C and D in the ratio of C and D small letters. Okay? I think you are getting my point what I am saying to now. For example, suppose this formation of reaction of ammonia, the formation of reaction of ammonia were known as the reaction said about the 3 mole of hydrogen combined together to 1 mole of nitrogen to give 2 mole of ammonia. That is a picture what we can see from the reaction. But is it true? Is it true to learn? This is one of the important one. The rate law and the rate expression actually explained about that any given reactants and their concentration, how they actually involve in the chemical process. Only practically we can observe to which extent the nitrogen and to which extent the hydrogen actually combine simultaneously to give this ammonia. Because in the reaction we can see only a 3 mole and 1 mole in the ratio, but actual picture is really different. The rate law will explain you about the actual concentration of reactants that will going to involve in any chemical process, and that will determine the rate of chemical reaction. For the same, the rate of chemical reaction can be written for this general reaction is like rate. Suppose the rate of reaction is proportional to this concentration A to the power x, where this x is actually indicating to which extent of the molar concentration of A is actually decide the rate of reaction. At the same time, rate of the reaction also depend to the molar concentration of B to some extent. Suppose that extent is Y. This power X and Y actually indicating the molar concentration of A involved in the rate of reaction to which extent. At the same time about B also. It means on conclusion the rate of reaction you can decide like the rate of reaction of this any generally given reaction is actually can be determined by it is proportional to the product of molar concentration of reactants to the power raised to their sum coefficients. These X and Y is experimentally determined extent value which may be equal to the A and B or may not be equal to the A and B. It is not confirmed, but it can be only determined by a practical experimental approach. By just theoretical knowledge, we cannot actually determine to which extent the A and B will really combine during a chemical process. We only can actually explain about, with the help of experimental data, how this A and B combine together to give us C and D, and to which extent that is given here X and Y. That's why I'm asking here this X and Y, the coefficients, the power actually indicating to which extent of A, the molar concentration of A is actually going to participate in the chemical process with the B to give C and D. If proportionality sign is removed, we can write like rate equal to K A to the power X, B to the power Y, and this rate can be written like this. This equation minus dr by dt equal to k a to the power x and b to the power y is actually called a rate expression for any given chemical process. And this is the differential rate equation formation. Differential rate equation formation where this dr minus dr by dt is a differential value for any given rate of the reaction, and this A and B is a molar concentration, and X and Y indicating to which extent of the molar concentration of A and to which extent of the molar concentration of B is actually participate in the chemical process. This is the rate expression actually. So we can define the rate law. We can define the rate law on the basis of this rate expression, and that is the rate law can be defined as when the molar concentration, when the reactants indicated in their molar concentration to raise some power. To raise some power is actually called rate law. With the help of this equation, you actually try to deduce the one picture about the reaction. For any given chemical process, the rate can only be determined to the combination of molar concentration of reactants to the some power. That power actually indicating the order of the reaction. That power actually indicating to which extent experimentally the reactants determine the rate of reaction. This X and Y may or may not be equal to the given real stoichiometric coefficient in the any equation. This actually equation, this stoichiometric coefficient actually given a complete picture, but not actually explained about to which extent simultaneously the reactants combined or collide during the chemical process. And that's why we have to learn about, with the help of experimental data only, how this reaction can be achieved. And for that we have one example given in the NCERT book. The one reaction is given. With the help of that reaction, we will try to learn what is the real picture is about the rate law. And therefore, the table 4.2 you can take from your NCERT book. You can open your NCERT book to see the table given 4.2, initial rate of formation of NO2, and with the help of this experimental data, we will try to write the rate equation, the rate law expression for this given equation. Okay, the reaction is this: 2NO plus O2 gives out 2NO2. This is the reaction, and the table there is given initial concentration of NO is given there. There are total 4 experimental data value given. For NO, the concentration of NO, the concentration of O2, the concentration of NO2 is actually given. You can see that with the help of experimental data first and second, the initial concentration of NO is double, 0.3 then 0.6. The initial concentration of O2 is constant, and the initial concentration of formation of NO2 become 4 times. Become 4 times means when the concentration of O2 remain constant and we double the concentration of NO, we will get a 4 time value of the NO2, indicating the second power, indicating the rate is actually depend upon the directly proportional to the concentration of NO to the power 2, because when we increase the value of NO twice, we will get the rate of formation of NO2 4 times. That is actually can be confirmed with the help of the data given in the table, because the concentration of NO2 become 4 times when we just double the concentration of NO. That only can be achieved by the power of 2. Okay, next one. When the experimental data of the NO become constant in the case of experimental number first and third, the data number first and third, you can see that we just double the concentration of O2, there is only a double value, we will get the double value of the concentration of NO2. It's mean the rate is directly proportional to the concentration of O2 to the power only 1, because when we double the concentration of O2, we will get the rate of formation of NO2 is also double. So that is just a directly proportional. So with the help of this value, this experimental data, we can deduce that the rate of the above reaction can be written like this. With the help of this experimental data only, we can try to solve the problem based on the rate of reaction, that rate constant and molar concentration value of any given reactants. Here in this reaction, you also can see that the power is also equal to the stoichiometric coefficient. This is the value of x, which is equal to the small a, and this is the value of y, also equal to the small b. So it may be equal to the stoichiometric coefficients, but it is not necessary for the all reaction it can be equal. It may be a different also. The conclusion is, for any given rate of reaction, the rate and that rate constant value and order of the reaction only is the experimental data. It can be only obtained by the experimental value because not of the any given reaction or any theoretical data. Same time, some of the more example given in the book, you can see that the examples number on the page number 102, there are given the combination of chloroform with the chlorine and the hydrolysis of ester. And both the data, you can see what is the real picture actually given. Chloroform. CCl4 and Cl. Rate law expression given for this reaction is rate equal to you can see the data. Look at the picture now. Chloroform combined with the chlorine with the same ratio -1 to form carbon tetrachloride and Cl. But actual process is, you can see the rate of the reaction depends upon the first power of the chloroform but half power of the chlorine. Coefficients given 1:1, but the rate determined that the rate of the reaction depends upon the molar concentration of the chloroform with the same power, but with the help of chlorine the rate depends upon to the power half. Half means that will be under root. Okay, and with that equation you cannot determine this value because this is experimental data only. With the help of experimental data we only can be reduced that there is a half power. At the same time, the next reaction given, the hydrolysis of ester. Hydrolysis of ester, the rate of reaction actually never depend upon the concentration of water molecules taken. The hydrolysis of esters always is actually the rate of reaction depends upon the molar concentration of esters only, not the molar concentration of water. But in the reaction, ester and water both are required for the given process, but the rate of reaction will not depend upon the molar concentration of water, and that's why you can see in the reaction the given equation given example given, the rate of reaction is the zero power of the molar concentration of water. Zero power means that value will become a unity, that is independent to the rate of reaction. This is some general informations and concept about the rate law and its expression. Now we'll try to learn what is the meaning of order of the reaction here. Order of the reaction. Actually, the order of reaction is just a sum of the power of the sum of the power given in the rate law. Given in the rate law, if rate is right like this, K so order of the reaction means to which extent the concentration of reactants are actually consumed during the process of the reaction or the course of reaction. It actually indicating the sum of the power used in the rate law expression. The rate law expression, what are the sum of the power used, that is just to tell about the order of the reaction. So you can just say that the rate of the reaction is dependent upon the x power of the molar concentration of A and y power of the molar concentration of B, and total order of reaction is called x plus y. It is just indicated by small n. Small n. If value of x plus y is 1 only, 1, so means order of the reaction is 1. First order reaction, that is called. If the xn plus y equal to 0, it will be called zero order of reaction. If x plus y is equal to 2, it can be a second order of the reaction. This is the one of the method to said above. The order of the reaction can be fractional, can be 0, or can be actually any whole number. Fractional, 0, or any whole number. Generally, the order of reaction goes to up to actually third order, because it is believed that the collision of molecules simultaneously occur up to 3 particles, and it is actually a very rare condition. Students, you should learn that simultaneously when the particles collide to decide the product formation, that is actually up to 2 particles. That is very easy to collide together. But when we call the 3 particles simultaneously collide to give a product, it is a very rare condition, because the collision of particles simultaneously, the 3 particles, decrease the rate of the process. That's why the third order and molecularity third is a rare condition. Generally we have a 0 first and second order, that will be very easy. But many of the reactions known where the rate of reaction, order of reaction is 0, fractional, first, second, third, and so many more. Okay, so for any given reaction, look at the possibility. If the reactants changes into product and minus dr by dt, that is called rate equal to k. This is called zero order of reaction. Same time, you should learn the unit of the rate constant value actually. Zero order reaction means the rate of reaction is independent to the molar concentration of reactants, because the molar concentration of reactants to raise the power 0, and you can calculate the unit of K, the rate constant unit. The rate constant unit. What will be the rate constant unit for here? The rate constant unit will be the unit of K will be, this is called rate upon the concentrations, the molar concentrations. You can see here the molar concentration. Molar concentration to the power n, where n is the order of the reaction. The value of rate means, you can see the concept possibility, the rate equal to the molar concentration upon the time taken. So this will be mole per liter in the terms of concentration. In the terms of pressure, this will be a bar or atmosphere, and this is called time inverse. So you can calculate the rate unit of K also. Here in the condition of 0, this is called 0 value. For the zero order reaction, the unit of K, the rate constant, will be same as the unit of the rate of the reaction actually. That is minus dr by dt value, which will give you a mole per liter second inverse. This is the unit of the reaction, a unit of the K, sorry. With the help of value of unit or the unit value, you can actually determine what is the order of reaction. Sometime in the numericals, the unit value is given, and with the help of unit, you can identify to which order of reaction they are asking about. You can see mole per liter second inverse is the unit of the zero order. The same way, you can write for the first order. Rate For the first order reaction, the rate of reaction will be to the power 1 of the molar concentration of reactant. So the unit of K will be the unit will be mole per liter cancelled by mole per liter, and the unit will be second inverse. So for the first order reaction, the rate of reaction will depends upon the first power of the molar concentration of reactants, and unit will be time inverse, sometimes second inverse, mostly sometimes minute inverse depending upon the condition. So it will be a time inverse value for the molar rate unit of K. The same way you can calculate the unit of the second order reaction also. And you can actually evolve the formula for the unit of constant for any given order of reaction, because it will just depend upon the molar concentration to the power n and the rate value. Okay. For second order reaction, suppose the rate equal to the unit of K will be the unit of rate equal to mole per liter second inverse for the unit of rate, and this will be mole per liter to the power 2. Mole per liter to the power 2. So the one value, the mole per liter, can be cancelled by mole per liter, and this will give you mole inverse liter So second order reaction, for the second order reaction here, the order equal to second. For second order reaction, the unit of K will be mole inverse liters second inverse. This can be calculated easily by the given rate expression. Okay. The next thing, some question given as an example, calculate the overall order of reaction which has the rate expression given there. So the overall order of reaction is just a sum of the power, the exponents there. The exponents given 1 plus 2, 1 by 2 and 3 by 2. 3 by 2 and minus 1. So you can calculate the overall order of reaction by just a sum of exponents value. The next thing about the table number 4.3, the table number 4.3 is actually asked about the unit of the reaction, unit of the K for the different order. For 0 order, you can calculate it mole per liter second inverse. For the second order, mole inverse liter second inverse, and for the first order, the second inverse value. This will be a different unit. Now the term we can discuss about, that is molecularity of a reaction. Students, molecularity means the number of species simultaneously collide in the rate determining steps. Actually, many of the reactions known where the reaction proceed in the one step only. These reactions called elementary reactions. Elementary reaction means the reaction proceeded in a single step without any splitting. For that, there is only that same step, that first step called rate determining step. But many of the reactions known where the reaction proceeded into the more than one steps, and for that we have to be write the mechanism of the reaction. Mechanism of the reaction. That mechanism of the reaction indicated, I think you have remember about in the organic chemistry when we decide to write the mechanism of the formation of alcohols from the alkene molecule. Have you remember the hydration of alkene to give out alcohol? That there was the 3 steps now. So out of 3 steps, there is one of the steps that will be a rate determining step. Actually, how can we calculate that the given step is rate determining? Always the slowest step is called rate determining step. And how to know that the step is slowest? It can be calculated, it can be seen, or it can be observed by the generally breaking of bonds. The step involved in the breaking of bonds is actually slowest. The formation of bond is always a fast step. But in this chapter, chemical kinetics, you have given a slowest step, and you should be remember that the slowest step will be rate determining step. So the number of species of reactants present in the slowest step is called the molecules that will actually give the rate of reaction and determine the rate of reaction. So the number of species or molecules involving in the slowest step or rate determining step is just called molecularity. It never be 0 because at least a single particle will involve in the rate of reaction. So the molecularity can be 1, can be 2, and some rarely can be 3. But it has been never seen the molecularity can be up more than 3 because it have seen that the more than 3 particles cannot be collide simultaneously to decide a rate of reaction, and that's why it is a very rare possibility to see the molecularity 4. So most of the reaction having molecularity 1, 2 or 3 depending upon the number of particles or species collide simultaneously. For any given reaction, you can see in the examples. In NCERT, example given, the decomposition of ammonium nitrite. The decomposition of ammonium nitrite, the molecularity is 1 because the only one particle involved in the rate determining step. Same way, the dissociation of hydrogen iodide, there is 2 particles, so molecularity is 2. And there is combination of nitric oxide with oxygen to give out nitrogen dioxide, the molecularity is 3, but it is a rare one. At the same time, some of the example more given, if any reaction you can see the more than 3 molecules involved, it must be a complex reaction. Complex reaction means all those reactions having more than one step to determine the rate of reactions, and in which the slowest step will be actual rate determining step, and number of particles or molecules involved in that species, that step is called a molecularity of the reaction. So you can just calculate the molecularity of the reaction by the given experimental data again, because without writing the mechanism of the reaction, you cannot decide which one is the slowest, and without knowing the slowest step, you cannot calculate the molecularity of the reaction. This is all about the reaction and equation. The next lecture, we will start the integrated rate equation. We will try to integrate the rate equation for the 0 order and first order given in your syllabus. And before that, we will try to calculate the in-text problem 4.3, 4.4 and some examples. So next lecture will depend upon the numerical approach of the order of reaction, molecularity of the reaction, and they then will derive the rate differential and integrated rate equations for any given first order and 0 order reaction that is given in your syllabus. That is all about the today's lecture. So I am concluding my lecture here only. We'll meet tomorrow for the next lecture. Thank you.